Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning or afternoon. So welcome back to SID3019. Today we're going to look at lecture number 10. Okay, another asynchronous lecture. So we are now on the 10th of May 2021. So next week we will not have any lecture. It will be your semester break, and then we will come back and we will continue our lecture for a little bit. Okay, and then on these 2 weeks, as I mentioned, it's a pre-planned lecture whereby I will have an invited lectures, but as of today I'm not sure whether it's still gonna be okay, since it's MCO and I have yet to get any feedback from NPRA. I know they are very busy analyzing vaccines and whatnot, so fingers crossed. Okay, and on the 14th of May we will have your second quiz, right? Okay, so anyhow, so if the 2 invited lectures were not able to give out the lectures, what I will do instead is to give you guys some tutorials, since it's asynchronous. So we will do a tutorial, a live tutorial, and we will see how it goes. Okay. Alright, as I mentioned previously, this is a teaching survey. I would be very grateful if you guys can actually participate in this survey. This is a recorded lecture, therefore the type of information is in division B, in case if you want to help me and my colleagues to do this survey. Thank you. Alright, so last week we've looked at a little bit, we did a revision on NMR spectroscopy. Okay, we looked at different 2Ds, NMRs, particularly COSY, TOCSY, and a few others. Okay, so today what we're gonna do is to continue option number 3. Okay, option number 3, which is how do you actually analyze peptides and proteins, and option number 3 is basically NMR, and it's actually very complex information. So this is a very brief, very general information on how you can actually do that. Of course, being a teacher in education, if you are really into it, what you can do is you can just find the books based on the references that I gave, and go into a bit more detail if you are interested. Okay, so as I mentioned, if you know that your structure, or given the information that you have a chemical formula and a carbonyl group, therefore if you deduct a carbonyl from the chemical formula, what you will get is you get a C7H16 and a C double bond O. So if you draw that one in the middle, okay, because I said this is a carbonyl, I didn't mention that there's a ketone or an aldehyde, but we'll just do C double bond O first. All right, now, so what TOCSY tells you are all the spins that are linked to one another. Okay, so what it means is that if you have a carbonyl group in the middle, of course the spin system will not be connected. Okay, so if say you have an aldehyde, for example, okay, then you have your aliphatic chains like that. So what we will see is you will see an interconnected spin system for all the protons. Okay, so meaning that this proton over here will be connected to that one, and then of course it will be also connected to the ones adjacent to it. Connected in the sense that or if you're gonna joke about it, it's more like, you can sense the neighboring protons, but well, it's kind of like that, but in the spin system whereby one proton is connected to another one. All right, so if you see these 2-dimension proton NMRs, what you do, the first one is to draw a diagonal line. Okay, so you'll draw a diagonal line. Of course, not all, for a normal simple molecule like this, you can draw a diagonal line, but for peptides and proteins, what you will see next is you will not always play around with a diagonal line. Okay, so what you do is first you draw it like that. So you know that all these peaks on top of the diagonal line corresponds to the major peaks that you see here. Now, what TOCSY tells you are the spin systems. So if you look at these two groups over here at the very top, what you'll see is, because this is a proton NMR, so you know that, well, there are two groups adjacent to the carbonyl. So you know that the carbonyl contains two different proton groups, or two different spin systems, because they are not connected to one another. Okay, and how do you verify that? If you follow the blue dotted line, okay, so you'll see that and that. That is all. Okay, so the cross peak only crosses to another diagonal group. So this diagonal group are connected to, or in close proximity, or in the same spin system as the ones over here. So you know that this peak and that peak over there are actually within the similar spin system. And if you follow the other one, you will see the same thing. Okay, so that one over there is connected to the one around, what was it, about 2.5. Okay, and of course that one also has the same spin system, and of course this one and that one are adjacent to one another as well. And you'll see the other one is this, and you know that this is connected to that one and that one and that one. Okay, so once you know that they are connected to spin system, because this one is 1 carbon, 2 carbon, 3 carbon, 4 carbon, okay, and because we have 8, 5 if you consider the carbonyl, so the fifth one is the carbonyl. Okay, so why I'm saying carbon is because all the protons are connected to carbon, so just consider them as the whole group connected to a single carbon. So 5 carbon, 6 carbon, 7 carbon. Okay, so if you where's the 8 one? 1, 2, 3, 4, 5, 6. You have 2 over here. Okay, because you can see this small dots one. So 1, 2, 3, 4, 5, 6, 7, and the 8th one is the carbonyl. Okay, so 1, 2, you have 3 and 4 over there, because you can see this is the another connecting dots. So there's actually 2 different environment protons over there. Okay, so 5, 6, 7, and carbonyl is the 8th carbon. Okay, so if you consider that, then you know that the blue ones, okay, this one is connected to just only 1, 2. So you know that you have 2 carbons at one side, okay, and the rest of it is over the other side. So you have 1, 2, 3, 4, 5, 6, 7, 8. Not that one. Okay, this one is protons. Okay, so now you can really verify that this is the structure that you have. Okay, without looking at TOCSY, you can still do that, but you need to look at integration, and then you need to try and figure out if this integration is for protons, then you know that it's a duplicate and it's a middle because it's multiplet, and so on and so forth. Okay, so this is one way. Well, again, I'm hoping that you have already covered this in your organic lecture, so this is kind of like a refresher. Now, how do you actually use this information in protein and peptides NMR? So if you were to do an NMR spectroscopy or proton NMR for a protein, for example, here is ubiquitin, what you will see is you will see a mass of peaks. Okay, so you will see, but again, it's a similar principle whereby you know a metal group is normally around 1 or less than 1, and then you can have an aliphatic groups. Okay, and then what you'll see here is alpha protons, because remember, when you have a carboxylic, when you have an amino acid like this, okay, so this is just a simple amino acid, but of course if you are talking about proteins and peptides, then you have interconnected bonds over there. Okay, you have the R group, and of course you will have your alpha proton. So this is the range whereby you can see your alpha proton. Okay. And then because you have the amide bond, then you'll see that, okay, the side chain of NH, yep, the amide bond NH, you'll see aromatic around the same range, okay, between about 6.5 to about 8. And then of course you can also see the backbone of NH. So there's two groups of NH that you can actually see. Now, so it's a complex nature. Therefore, by just going through one dimension NMR spectroscopy, it's very difficult to identify your proteins, especially if the proteins are new proteins. It's impossible to actually know the sequence of the protein by just using NMR. Of course, if you combine with mass spectrometry, for example, then yes, you can identify the sequence of the protein or peptides, but this lecture is specific for NMR and how you can actually validify the sequence of your NMR, of your protein or peptides using NMR. Okay, now Woodridge and co-workers in early 1980s, whereby at that particular time NMR spectroscopy kind of like and one of the emerging techniques. Okay, so it's very new, it's very recent. So what they did was they identify how you can actually do all these steps and processes to know proteins and peptides. So if you go and find the articles that they publish, so they actually went into very detail on how you can actually use NMR to identify protein and peptides. And the method that they publish is called as homonuclear proton method, the sequential assignment procedure. So they actually mention how do you actually do that one by one. And in 1983 they also publish so this is the paper, and they actually publish another book on in very detail, a bit more detail on how you can actually do that. So in this manuscript, basically what Woodridge and the co-workers did was to use the J correlation spectroscopy, which is COSY and TOCSY, to identify individual spin system. Okay, scalar coupling. So we'll look at scalar coupling. It's just another revision, and to use NOE spectroscopy or NOSY to link the amino acid in sequence, dipolar coupling. So what are the differences between scalar and dipolar? Scalar is connecting through bonds like that, okay, and dipolar is a connection through space. Of course, for NMRs, the backbone needs to be connected, otherwise it will be a messy NMRs altogether. Okay, but imagine in 1983, so it was a long time ago, that these people, these brilliant scientists, managed to develop methods to actually identify and look at protein and peptides. So basically, to summarize what they identify or involve in these three simple methods. Okay, the first one is to identify of amino acid side chain spin system. Okay, so what we will do here is we'll just to cover it just in very brief as a to-know basis for you guys. Okay, as to-know basis, and of course I can ask it in your exam or your quiz. And once you have identified the amino acid, what you do next is you identify the neighboring residues of the protein sequence or peptide sequence, and then number 3, you find a suitable combination of the results from 1 and 2, on which provides individual resonance assignment to the primary structure of the protein. So what you'll do first is you identify, say this is the length of the peptide of protein. First is you identify one of the protein or amino acid within the protein. Okay. Then number 2, you identify what are the adjacent ones. And number 3, you use the information to keep on looking at adjacent, identify and adjacent, to actually go and walk through the backbone to actually identify the peptides or protein sequence. Okay, so it's actually very a unique ways of identifying protein and peptides. All right, so the first one, okay, so first identification of amino acid. So by looking at the spin system. So what is a spin system? It's basically a group of protons that are connected between one another. So normally in your lecture, probably your lecturer mentioned it's normally within 3 bond length. Okay, so that is what we call as scalar spin-spin coupling. Okay, or scalar coupling or J coupling. Right, so J coupling, the J values that you normally see if you have, remember, if you have a triplicate, triplets, for example, you can actually analyze what is the J coupling, J value for between the two peaks from of a NMR, and then from the J value you can see whether it's vicinal or geminal protons. So this is what J coupling is. So what you do is you are actually looking at a connectivity, these protons that have the same spin system. Okay, each amino acid is composed of one or more spin system within the peptide bond separating them. So because of the presence of amide, okay, like that, oops, okay, and of course we have a peptide there. So again, you have a carbonyl group between each amino acid. Therefore, the spin system within the amino acid itself is considered as one. So it has its own spin system. Okay, so the spin system of the non-labile proton in HC alpha R can be classified as, so R is the side chain as I'm drawing here. So these are just the naming system that they use. It's a bit more complex. This is just to let you guys know a little bit about the ways of spin system, naming of spin system in proteins and peptides. Of course, it's no longer widely used, but nonetheless, this is the basic. So so X is the alpha protons. Okay, so you have alpha protons over there, and then the alphabets next to it is the alphabets which is related to the R group. Okay, so even though glycine, if you were to draw the chemical structure, it's basically, oops, something like that. Okay, so you have 2 protons, but instead of writing it as x squared, x2 or a2, what the spin system does is x and a. And if you can see, for alanine that has a methyl group, then it will becomes a3x. Okay, again, that one is from the alpha carbon, hydrogen connected to the alpha carbon, and then the A3 is the proton spin system connected to the alpha carbon. So they can see each other, they can sense one another, and therefore if you really look at the connectivity via TOCSY, for example, you can actually see them. Okay, similarly, when you have a more complex system like serine over here, so because you have another proton over there, so you have the alpha carbon, and then you have M, which is related to the middle bit over there. Okay, serine, you have the R group, so if you consider that as carbon alpha, so you have it like that. Okay, and of course you have H2 over there. So this is the M, and then you have the outmost proton as an A. Okay. Similarly, cysteine will have the same spin system as a serine. Okay, valine, because you have two branches, then you have A3 and B3. Again, M, signifying that you have a CH group in the middle there, and then X from the alpha. So as you go to a higher, more complex amino acid, the spin system naming will be more complex as well. So I'm just going to show you this for now. So to look at it in a different perspective is by doing by looking at the connectivity via well, we'll go into it in more detail. But what it does tell you is that when you are looking at the two-dimensional proton NMR, you will see the NH group, for example, are connecting to these two spin systems. So one is the X and the other one is A, in case for glycine. Okay, so that's why you have A and X as the spin system written here. Similarly, for a valine, you have X, M, B3 and A3. So you have so this one is most likely, this one is the X, okay, and then you have the M, and then you have the A3 and B3. Okay, well, of course I'm not sure which one is which. You need to identify by looking at the vicinal and juvenile protons. Okay, so that's the basic system. So basically you are looking at the NH group, the amide group, and what are the connecting protons. So whatever is in here is considered as the same spin system. All right. So if you look at COSY and TOCSY now, so COSY, as we mentioned last week, it's a correlation spectroscopy. So COSY display proton-proton correlation due to scalar coupling. Again, different another terminology, scalar coupling compared to a dipolar coupling, which is more space connectivity, okay, or adjacent in space. So its efficiency of coherence transfer decreases with increasing line width. So as the bonds or the connectivity get further and further, the signal transfer decreases. Therefore, if you are to look at the scalar coupling between the NH group to the furthest away, okay, the peak over here will be quite small, okay, but you can still see it. As the peak gets nearer to the proton of interest, then you can see the peak is bigger. So, but this figure over here is just to show you in a theoretical manner. This is by no means the experimental. I'll show you a little bit on the experimental soon. Okay, so it's the COSY spin system in peptides are normally used for a smaller peptides, okay, because it will be less complex. If it's more complex normally, especially for identification of proteins, huge proteins, normally what people do is when they synthesize it using bacteria, for example, what they will do is they will put a label nutrient sources. For example, they will put in an increased amount of carbon-13 inside the growth media so that the bacteria will actually use a high amount of carbon-13. Therefore, your backbone will be more labeled, and thus it's easier for you to run your NMR. Okay, so COSY can be classified based on the regions. Okay, what do I mean by that? We will look at it soon. Okay, so basically, in a simple manner, is basically this. You can have your NH region, you can have your alpha proton region, and you can have a different region based on the amino acids. Okay, so these are the 5 or 7 regions. 1, 2, 3, 4, 5, 6, 7, 8, 8 regions using COSY spin system in for peptide and proteins. So basically the regions are as well separated within the COSY 2D spectrum. Alright, so you can see here you have A region up here. Okay, so that's the A region. You have B, C, D, E, F, G, and H. So each region corresponds to one unique feature or identity, which is A is for non-labile, non-aromatic alpha proton, sorry, not alpha proton, side chain proton, except for threonine, proline, and serine. Okay, so B is for this, C, and so on and so forth. All right. So these are all the regions, but the most important thing, the most important region that normally we use is the G region, which is the backbone of the peptide or proteins. Okay, so it's more of a fingerprint region, and this region is the one that we normally use. Alright, so fingerprint region, each amino acid except proline will show a single peak at that particular region. The NH terminal amino proton will not be observed due to rapid solvent exchange. So meaning that at the final, so you have a lot of amide bond in the middle. Okay, so you will see all of these in that particular G region. Okay, but the N terminal is not observable because there will be a rapid exchange of proton with the solvent peak. Okay, so which is deuterium. So once you get that substituted by deuterium, then the signal will no longer appear. Okay, additionally, proline signal is not observable because proline only has one. Okay, so that is proline. Okay, so proline is a more a cyclic amino acid, and it's connecting to the same amide bond. So proline does not have any protons that is observable by looking at COSY spectra. Okay, so again, scalar coupling less than 3 bond length is observable. So in practice, less signal may be observed due to signal overlapping. As you can see, in Ubiquitin NMR that I've shown you initially. Okay, so the signal can be very, very massive. There will be an exchange of broadening of proton. So, and it could also be a small J coupling. Alpha helix coupling is constantly at less than 4 Hertz. So this is based on the structural motif of the protein or peptides. But what COSY can tell you is that the amino acid of interest only, and not the protein and peptide sequence. Okay, if you're just looking at COSY, it will not tell you anything. Similarly, if you're just looking at TOCSY, it will not tell you anything. If you look at any singular 2D NMR spectroscopy, it will not tell you anything. Okay, so this is the first step. So still, we're going to look at this is just another slide telling you guys about the regions and what the regions correspond to. Okay, so fingerprint region, so alpha, the amide protons to the alpha hydrogen. Alright, so TOCSY, on the other hand, total correlation spectroscopy, it completes resonance throughout the spin system. Okay, only on the space system. So anything that is linked to within the same amino acid. Okay, special case for aromatic spin, for example, phenylalanine is not connected to each other, resulted in 2 spin system. You will see next. And tryptophan, for example, you have a 3 spin system. Alright, so the spin system for tryptophan are, so if this one is an amide, okay, imagine this one is an amide, so that is 1 spin system. Okay, and then you have this as another 1 spin system, and you will have that protons over there as another spin system. So you will have 3 spin systems. Okay, so backbone component of 2 spin system, aspartic acid and phenylalanine, as shown on the left. So if you are to look at the 2D spectroscopy, the spin system looks almost identical. Okay, so you can see for aspartic acid, it will be like that. Okay, because the backbone are almost identical. Alright, so that are the spin system. Okay, so that's the basic spin system. All right, and additionally for phenylalanine, what you will see is a smaller subset of spin system. So if you see a spin system like that, and then suddenly you see, oh, there's another spin system in the middle. So it's a quick identification that this could be a phenylalanine. Okay, so TOCSY, what it does tell you is it talks about it can tell you about what are the amino acids, but it doesn't tell you what are the adjacent amino acids. So you can identify amino acids. For example, if you look at this TOCSY, this is how the spectra will look like in a real practice. Okay, so it's kind of like a 3D contour. The image is a bit bad, but it's actually like a 3D contour. Okay, if you look at maps, normally you'll see like this. Okay, so as you go in the middle, as you have more bands, then if you were to look it from the side, it looks like that. Okay, so something like that, it's like your 1D NMR, correct? So it's just based on the peak high and so on and so forth. So the higher the peak, meaning that there is more protons there, and because this is a 2D system, means that they are connected to close proximity. Okay, all right, so what you can see here is this one is the alpha proton. Okay, and then throughout the spin system, because this is TOCSY, so they have the same spin system. Okay, so what you can see is you can see the alpha proton and its connecting spin system. So what you see here is a beta. Okay, and then this one is gamma, I think, or epsilon, sorry, epsilon, gamma, and delta. Okay, so as you go further, then you have a higher and higher spin system, right? So what this tells you is that if you look at this particular fingerprint, okay, so there's no other amino acid that will have the same fingerprint. So you have alpha there, and then another 4 in this particular density. So beta, which is very high dense, and then another one which is a very high dense, and then the smaller ones and the smaller ones. So this identifies that this sequence is isoleucine. Okay, similarly, if you look at another spin system, so this is a different amino acid. Okay, that one is connecting to this one, so that one is the hydrogen alpha. Okay, this system is leucine, not valine, leucine. Okay, and then if you go to the next one, again, that's the hydrogen alpha, that one is valine, and so on and so forth. Okay, this one is histidine, for example, and then glycine, because it has no chain or aliphatic chain on the R group, is actually just a singular a single broad peak. Okay, so that one is glycine. Okay, and this is just a summary of how the fingerprint looks like. So we've looked at valine, for example. Wait, the first one was isoleucine. So if you look at isoleucine here, okay, you have your alpha, and then you'll have your beta, gamma, epsilon, and delta, which is close proximity, as what you've seen here. Okay, we've looked at valine, for example, another one. So valine is down here. You have your alpha, and then you have your beta and gamma straight away. So, but over here you don't see the other ones. So beta is observable, but gamma might be somewhere at the top. Okay, so this is just an example of how you identify the amino acid using TOCSY. So TOCSY is very, very easily identifiable. But again, it doesn't tell you what amino acid is next to the other one. So just to compare between the two spin systems, by doing COSY, what you will see is just this. Okay, but if you actually do TOCSY, you can see the spin system throughout the side chain. So that spin system are similar. Okay, you can see 5, 1, 2, 3, 4, and 5. But you don't see the other spin system. Okay, so so region containing amide protons, F2 vertical, so that one is F2. Okay, and aliphatic proton, which is F1. Okay, for COSY on the left hand side and TOCSY on the right hand side. So COSY and TOCSY identify the amino acid of interest only and not the protein and peptide sequence. So this is just to reiterate what I've mentioned at the last slide of COSY. Okay, so you can identify the amino acid, you can know what is the amino acid, but you do not know. So that one is one amino acid, that one is another one, that one is another one, that one is another one. Okay, so something like that. All right, so let's move on to the neighboring residue. So how do you identify the neighboring residue? So you identify it by using NOESY, or nuclear Overhauser effect spectroscopy. What NOESY tells you is a cross peak showing a dipolar coupling, so space coupling, approximately around less than 5 angstrom. So but because of the dipolar coupling, therefore you can also sometimes, not always, see the same peak overlapping from COSY and TOCSY. Okay, but of course not all say for example TOCSY peaks are available on NOESY, and not all NOESY available on TOCSY. Why? Because TOCSY is throughout scalar coupling, so everything that is connected, then you will see it. But NOESY, you only see something which is close in proximity. Okay, for example, what you will see here, say for example, you have this amide proton over here, so Ni. Okay, so you have one proton, and then this one is Ni plus 1, meaning that this is the adjacent amino acid. So you will see a dipolar coupling between the amide protons. So what we call is dipolar coupling of N to N. Okay, so we'll see coupling from the N to the alpha hydrogen, of course. So you call it as D alpha N. Okay, and then you also see the D beta N, but you might not see the gamma or epsilon. Okay, so you might not see it. You might see it, but you might not also see that, depending on the situation. Okay, so what you will see in the NOESY spectra is basically one coupling. So you can identify the dipolar coupling between one amino acid within amino acid. And additionally, because of the alternating configuration of the R groups, okay, so if you draw peptides, you always draw it as something like that, right? O, so N, so R. So it's an alternating sequence. So it's going up and down, up and down. Of course, it's not up and down per se, but it's always kind of like opposite to one another. Not always, almost always going opposite to one another. So what you will see is a close proximity between the R group and the amide. The proton amide adjacent to the amino acid that you are looking for. Okay, so what additional peak that you will see when you have a NOESY experiment is you will see a connecting cross peak. Okay, and we will see how you actually use that. So similar to COSY and TOCSY, you do have a fingerprint region that corresponds to an identity of the peptides or protein. Okay, so you have for NOESY just 6 fingerprints. Okay, so you have A, B, C, D, E and F region. Okay, and it's correspond to all of these, so I'm just not going to read it because we are lacking in time. We don't have enough time to do it. All right, so and so moving on to the third steps. So the first step is to identify the amino acid by either using COSY or TOCSY. TOCSY is even easier. Second one is to just look at what are the amino acid adjacent to it. So the third one is to use information from number 1 and number 2 to actually do a backbone walk. Okay, so TOCSY can be used to identify the first amino acid, as I mentioned. Okay, but it's random, so you don't know where is the amino acid, especially if you have if you're analyzing proteins or peptides that have 2 or more similar amino acid. So basically what you will see is you can identify the amino acid, but you don't know which amino acid it is. Okay, but usually select the simple amino acid. So what you are interested in is you interested in finding any one of these as a starter. So say for example, if you have a very very long sequence of amino acid okay, just an example, serine, serine, glycine, lysine. Okay, so if you have a sequence like this, you do know the sequence by doing by looking at, say for example, the mRNA or any other information. You can know the sequence of the protein, but now what you are interested in is to look at what are the correct arrangement, and then based on that you can actually do a little bit more. So what I'm doing now is just to look at NMR and how NMR helps you to identify the sequence of the protein and peptides. But what you can actually use is to actually predict how the structure will look like, whether the sequence forms alpha helix or a beta sheet, or it's just a random coil. So those are the things that you can do, and therefore based on this information, instead of doing a crystal structure and solve a crystal to get the crystal structure of a molecule, what you can do is you can also use NMR and you can observe the structure of the proteins. So which is very interesting because X-ray, you know, is a crystal, so it's more of a static nature of the molecule. However, if you do NMR, because NMR is in a solution, excluding solid phase, of course, so you know that the protein is actually a dynamic, so it's not the static molecule. Therefore, doing a solving structure using NMR spectroscopy can give you a totally different result than what you would get if you actually do X-ray crystallography. Okay, so the pattern generated by TOCSY, interaction of the amide and alpha proton and amide and the side chain proton. Okay, so TOCSY looks at that, but NOSY can also look at this. So by looking at this, and then you can look at that, so you can identify what is the amino acid. Okay, so overlapping TOCSY and NOSY spectrum can be done to do a backbone walk. So I'm just going to read all these. Consider from TOCSY 4 amino acids were identified. So this is just an example. So from TOCSY, okay, remember this is TOCSY. You can just see the amino acid sequence, or you can only identify the amino acid. So say for example you have identified this amino acid, leucine, alanine, ASN is aspartic acid, and then glycine. Asparagine, sorry, ASN is asparagine. So how can you determine the connectivity? So by looking at both TOCSY and NOSY. Okay, so that one is TOCSY, that one is NOSY. So of course TOCSY, you look at it and then you manage to identify this peak correspond to what amino acid. So without TOCSY, it will be a bit difficult for you to identify that this one is leucine, alanine, asparagine, and glycine. Okay, so you use TOCSY, but because the F2 peak has similar chemical shift, then say for example if glycine, the NH for glycine is say 6, then you know that the same peak over there is also 6. So that's how you can identify this peak is glycine and that one is also glycine. So if you can actually overlap these two spectrum together, then it will definitely tell you, oh, this is glycine. Okay, so so that's why I said overlapping spectra. So inter-residue correlation, orange, can be identified. Okay, so for example, now if you look at glycine, you can say, oh, glycine is connected to leucine. So you know you have glycine, because the only connecting bond for glycine is leucine. So you know that glycine is either at the N terminal or the C terminal. So you either have G and then L over this side, or you have G and then L over that side. And then what else you can do is you can actually see that alanine is also connected to leucine. Okay, so you can either have alanine over that or alanine over here. Okay, so of course you can see that, and then you can also see this alanine connecting to a different peak of the leucine. All right, and glycine similarly, this is how you validify. So you don't just look at one peak and then you say, oh, it's that one. So you actually look at a few, because each of them will have what do you call it, overlapping peaks. Okay, but if you look at asparagine over there, it's not connected to anything. So asparagine might not be adjacent to this sequence that you get. Okay, so finally, just based on this, you know that your sequence can either be GLA or ALG, because you know that G is not adjacent to A, that's for sure, and L is adjacent to both G and A. So you can have either these two sequence. Okay, so that is the basic information whereby you can use this. I will just stop here and continue the lecture next week. Okay, thank you, and see you guys the week after. Bye. And for those who are celebrating, Selamat Hari Raya, and those who are not celebrating, happy holidays. Thank you and goodbye.